Okay, thanks, Janssen, for putting together a very nice workshop so far. Thanks also for the coveted last talk of the workshop, right before lunch and 20 minutes late spot. First, I assumed it was because I was a big draw, everybody would be here, but that's not the case. Okay, so in my ongoing effort to maybe increase collaboration among the three groups, I'm going to talk about not a finished story, a starting story. It's very, very preliminary, which actually is going to make it kind of an easy talk. I would love it if at least the PIs did this. I want to know what Heim thinks before he's telling us about the complete replica symmetry breaking solution. But of course, I risk saying something very stupid, so be a little bit kind. Actually, risk saying something a little trivial, which was even worse.
Did you use slides?
What?
Are you going to use slides?
I'm going to use slides, yeah, because I don't have any. I have even fewer results than last time. Okay, so I'm going to start with something that's kind of obvious. There's a huge amount of diversity in the brain. You guys can make your own list. One of the big things that struck me is excitatory and inhibitory neurons. It's the dumbest thing in the world to do. But we have other things. There are many neuronal subtypes. There are many synaptic learning roles. There are multiple layers. There are many areas. There are many different connectivity structures between layers, between areas. And it goes on and on and on. Okay? And the fact that there's diversity is hardly a surprise, right? I mean, we don't know for sure, but it's likely it simply makes things more efficient, right? We wouldn't expect, for instance, an iPhone to be homogeneous, and it's not, right? Because it's got different parts. It's barely a phone, but it's kind of a phone. It's a computer. It's got memory. It's got all sorts of things. It seems things simply break up, okay? So that's not a big surprise. The question we want to explain is...
Is it your computer or the connectivity?
I do not know. Okay. The question we want to ask is, can we explain the particular diversity in the brain? This isn't really the kind of problem I usually work on. I usually think about the particular computation the brain does. What I'm doing here is channeling Larry Abbott, who's kind of a genius at answering these kind of why questions. It's not like I don't like doing this, but he always picks them off before I even think of them. In fact, I talked about this a little bit, and he's already slightly working on this one too. So, but it's a sort of a big area, okay? And I'm not going to answer this question. What I want to talk about today is what I think is a promising methodology for getting at this question, okay? A little bit more background before I actually start my talk. So this is the parameter space of the brain. In the humans, it's an order of 10 to the 14th, all the synaptic connections. You can add all sorts of things, single cell properties, dendrites. It's pretty big, right? But a point on this space is your brain, and at birth, you're somewhere down here. If you're in many animals at birth, you do pretty well. If you're human, you're kind of a useless blob, right? Infants can't do much of anything. But sort of decades later, you come childbearing years, all goes well. You're a highly functioning organism. Okay? There are other members of your species, and if you happen to have kids, you're back there. Maybe we should just have lunch. Okay. If you're back here, right? And there's big evolutionary pressure to have this starting point, in some sense, better from one generation to the next, right? And this is kind of how evolution worked. The amoeba started off down there, and over several billion years, we end up with a human. Maybe some days we'll have a better human, okay? But there's 2 points. One is evolutionary pressure to make us better, and the other is that this massive loss of information, right? And my claim, which I don't know if it's correct, but I have the gut feeling it is. So Alex Pouget has gone. I collaborate with Alex Pouget a lot. He's always saying, Peter, I know this is true without doing any analysis whatsoever. Fortunately, he's right a lot. I'm hoping I'm as right as often. But if we want to understand the structure and diversity we see in the brain, we need to look at this implication of this incredibly wasteful step of having kids, right? What we really want is every 30 years a new body. We don't really want to have kids. Depending who you are. This is what I want. Okay. So the basic idea I'm going to consider is really simple. I mean, given my introduction, you probably know what I'm going to say next. We're going to have a standard setup. We have a network of neurons. It's got input. There's a network output, okay? The desired output. And we can train this network using some kind of learning rules and train it over. It gets better and better, input-output function. So the slight added twist here is, I'm going to lift this up for those of you in the back, is that we're not going to start off with deriving learning rules. We're going to learn the learning rules from scratch, along with other network parameters, and learning is going to occur in evolutionary timescales. Okay, it's hardly a new idea, right? These sort of genetic algorithms, evolutionary timescales, have been around for a while. In fact, even applied to the brain. So after we started this project, in fact, it took me a long time to decide whether or not to talk about this. But after I decided to talk about this, I found this paper, Learning to Learn by Bengio. I don't know who the other Bengio is. Claudia? Samia. Are they brothers? Brothers. Okay. So there were a couple follow-up papers, but as far as I can tell, there hasn't been much work in this area. I'm going to actually tell you the sort of main results of this paper later on. There's also sort of the machine learning community, sort of the artificial network community. More recently, has been looking on how to optimize architecture and hyperparameters, right? So for those of you who do deep learning, you have lots and lots of choices, and more choices as time goes on. You have to optimize a lot of things. What architecture do you use? What hyperparameters do you use? And they're trying to learn this, and the key thing, of course, is to make everything differentiable. And this is one paper out of many. But the goal here in this work is just to make networks learn better, right? With no sort of necessarily an insight. But we're interested in something slightly different. Okay, I'll read this up. Which basically what this approach can tell us about brain structure. Okay, so it can be kind of nice to derive super good learning rules, right? But the motivation is really about the brain. So what this kind of approach tells us about the brain. Okay. A little more detail. So we're going to have to sort of build some sort of starting point of a model. What do we need? We need a parameterized model of a network. Okay. We have to decide what to learn on evolutionary timescales and how to learn it. Okay. So if we have these three things, we then have ourselves a math problem. And once you have a math problem, maybe there's a chance at help solving. So I'm going to use a kind of standard model of the brain. It's got n neurons, but I'm going to divide it into k groups, something like this. So these could be layers, these could be areas, these could be excited or inhibitory neurons, different subtypes. We're just thinking of groups of neurons. And each group of neurons has some property in common. We're going to connect some subset of these, just like in the brain. We have some input and some output. Okay? Pretty standard setup. And the goal is for a given input-output function. So I'm going to specify, it's going to be supervised learning. And at the very end, I'm going to talk about what kind of output signal I'm going to be most interested in. So supervised learning, we want to learn everything, right? We want to learn how many groups there are, number of neurons per groups, intergroup connectivity, learning rules, and initial conditions. Okay? So we sort of want to learn from scratch how to build a good network to do something, okay? Which is exactly the problem faced by organisms over the last 3.8 billion years. No. I mean, so one of the big, hard problems in this approach is, I'm going to talk about this at the end a little bit, is deciding what the input-output mapping is. It's changed dramatically. Okay, in the old days, evolution was easy because you didn't have much competition, right? The first creatures that evolved something. Well, I don't know, there are other things, but certainly things have changed a lot, right? We have to interact with other species, and things change. But so this is a really, really hard problem, is deciding what to choose for the input-output function.
You say for a given input.
Yeah, so we have to choose it, right? We have to choose the input. I mean, that's the goal, but this is a big part of the problem, choosing the input-output. Say it again?
Why not randomly choose a problem set of a very large set for every generation?
Well, so we have to learn. Yeah, but so my guess is the answer you're going to get is going to matter. It's going to depend a lot on what you choose, right? How much information is it? So I'll jump ahead. What I really want to have is a very low information rate input-out feedback. Okay, so supervised learning. So there's a target output and the actual output, but I want the target output to be, maybe valence. Is this good or bad? Something really low bit rate, and you learn that. But I mean, it's a huge choice, right? And what you choose is going to have a huge effect. We saw this yesterday when Shay talked about, you change the input-output function and massively changes the learning.
But still, you assume that there is some representation of the input, which is, I don't know, periphery or something, which is fixed.
Yeah, it's fixed. In real life, of course, the input ultimately depends on the output. But as a first, so I mean, this is a whole program. As a first pass, we're going to fix the statistics of the input-output and let the thing learn. And you can imagine multi-agent versions of this.
But about evolution.
In evolution, it changes over time, right? It certainly changes over time, but presumably slowly, right? What do you say? Most of the time slowly, every now and then rapidly. Okay, so now we need to choose a model. I'm going to start with thinking sort of just for concreteness, thinking about a really simple model. There are no spikes. In this part, you can sort of easily modify just some kind of rate model. The difference is this X is a whole population. Okay, it's one of the, so X is sort of all the neurons in one of these groups. And the connectivity matrix is basically a matrix of matrices, right? So it's the connectivity from population J to population I. I'll be a little more explicit in a second. There's some output. We could put a nonlinearity around that if we wanted to. Class of learning rules, and this is going to be super important, right? So right now I'm writing sort of the simplest possible learning rule. It depends on pre- and postsynaptic activity and maybe a global feedback signal and a bunch of parameters. And the goal is to optimize those parameters to make the learning rule work as well as possible. Okay.
So you have no connections within the population.
Say it.
So within a population there could be...
No, there are connections within a population as well. So there's also, the diagonal terms, WII. And then I think something that's pretty important people haven't considered is initial conditions. So basically, sort of you're going to train this for some kind of a generation, and then at the end of it, just like when we had kids, we reset to initial conditions, and these, of course, are going to change, evolve in time. Okay, so to be clear, so this matrix here, W, each of these WIJs is this term here, and that, of course, has, so this is WIJ, the connection from neurons in group 3 to neurons in group 1, it's neuron N in group 3 to M in group 1. Okay? So the initial conditions are a little bit different, right? Because basically, and we'll get back to the reason for this. I mean, it's sort of obvious now. So each of these, this is a matrix, but it's all the same elements, right? And the reason for that is, if we didn't have this, some kind of constraint, when we, at the end of a training epoch, we would just keep this weight matrix here, right? The idea is at the end of when you die, when you have kids, your kids actually are reinitialize their weight matrices, okay? And it's going to be an important part of this whole program. I think it's actually a big constraint. So now we're going to get to what obvious training is divided into generations. So each generation, there are T trials. T could be a random variable. It doesn't really matter. The network gets input I. Its goal is to produce a particular output I star. And the weights evolve according to this preset learning rule. Should minimize some cost function. Okay, hopefully, if all goes well. But we don't actually choose the weights to minimize the cost function, right? This is just our goal, and that has to be done in evolutionary timescales, okay?
Peter, I don't see what's this division into groups where it enters. You could just write it as one.
So it has to do with resetting at the end of so we're going to train. I'll answer that question in just 2 seconds, okay, or 30 seconds.
Now there was no meaning to these groups.
Well, there is meaning to this groups because different groups have different properties, right? So these weights may have very different properties.
No, but
and different
within the group.
What's that again?
Within the group.
Within the group, it's. I mean, learning happens within the group, but so initially within the group, there's no structure. So this could be all the neurons in a.
Learning works on all connections.
All connections, so both within the groups and across groups.
So IJ is neurons, it's not groups.
So IJs are groups. So MN are neurons within the groups, okay? So theta I, so basically.
IJ. What is WIJ?
So WIJ, so this is basically a whole, so this should maybe, we could add an MN here.
Also it's a matrix.
So yeah, this is the matrix and MN, so this depends on MN. So this should be XI, comma, M, and XI, comma, N, XJ, comma.
So everywhere you have both IJ and MN.
Yeah.
So it's like.
They're not theta.
Say again?
Theta? What about
But not theta. Theta is very important. Theta depends only on I and J. Theta depends only on the groups, and then the condition depends only on the groups. Sorry.
So there is
Okay.
some.
So yeah, so different groups get different, and we see this, right? The inhibitory plasticity is different than excitatory plasticity, right? And long range plus.
Connections within a group, let's say they have one test,
Yeah.
not many tests.
Yeah. And the idea is, these groups are defined genetically, and so that presynaptic genetics and postsynaptic genetics determines the learning rules, determines initial connectivity.
But it's not true. Like you can take two pyramidal cells, they will have plasticity rules which may be faster, slower. They may have different.
Plus noise. We got a little bit of noise here. And noise, I mean, seriously, you're going to have to put noise in there because, gene expression isn't the same in every cell.
Well,
It's
different
massive
groups
diversity.
also.
Say again?
They have different learning plasticity.
Yeah.
Different groups.
Yeah. But I mean, so you sort of want that theta ij plus. Well, you don't want them to have too many groups either. We'll get to that in a second. But you really want to have theta ij plus noise, right? Just like you had noise here. I should have added. But that's a good point. So training's divided into generations. Wait, I've been over. Oh, I went back already, right? So after each generation, we reset the weights, right? So wij goes to mu ij plus noise. That's sort of this step. So along here, we train, and then we reset to a potentially different value. And we also update the parameters. So theta, the parameters change a little bit, the weights change, the initial conditions change, and maybe you shuffle neurons around groups, add neurons, subtract neurons. Okay? And obviously, conceptually, again, it's an old idea, right? So what's slightly new is we're applying it. We're really serious about applying this whole program to neuroscience. And we're also going to be very serious about the bit constraint. So we can't use too many bits to specify these parameters. There's some bottleneck of going through the genome, right? Maybe 10 and it's hard to know how to count. There are about 20,000 genes in humans, about 10 to the 9 bits, maybe. Not all of them used for the brain. So following is a bit of a bit counting exercise. So we have to make sure that we're not passing on too many bits. And sort of the worrisome is this thing, right? How many bits do we need to put neurons in groups? And if we had to specify which group each neuron went into, that would be order n bits, right? Which is certainly for humans with 10 and 10th neurons, that's too many. But in fact, we just need to specify how many neurons are in each group. Okay, and that takes far, far fewer bits. Basically, we have to ask how many different ways are to make k groups. We have to have a little math here, right? So basically, we have n1, this is 4 groups, so the n1 plus n2 plus n3 plus 4 adds up to n. And the different groups are determined by different partitions. So basically, as n choose k minus 1 are the number of ways to arrange the partitions. And so in the large n, small k limit, that's basically order k log n bits. Okay. So this is why we can't have too many groups, right? So k sort of has to be small. And it is. So in the mouth brain, there's something like 500 different areas. Multiply by 6 for layers, and you get on the order of something that's reasonable. Okay. For these parameters, it's order k squared bits, right? First of all, it takes about a bit to decide whether two groups are connected. Maybe a little less if it's sparse. But if they're connected, you need several bits to specify, the learning rule and the initial conditions. Okay. So we're doing okay for bits, but there's something that's sort of immediately clear from this, and I thought about this for a long time, hoping I could get something very, beautiful and general out of this. I've not been able to, but there's a trade-off, right? You can have, lots of bits for your learning rule and not much for initial conditions, and that would be a good learner, but a slow start, right? Presumably that's why humans are useless blobs when they're born, well, presumably. It's a complete guess. But it'd be really cool if it turned out that basically evolution devoted a lot of energy into giving us really, really good learning rules, initial conditions, and structure, but not much energy into setting our weights when we're born, right? Which is a big contrast to other animals. Insects, for instance, do pretty well at birth. Even horses in a couple hours can run around, right? Takes kids like a year-ish. So there's this bit constraint, and I think this is going to actually play a big role. Again, I'm sure it's going to play a big role, but I have no idea. So from the point of view from bits, we're okay. And so in some sense, we could stop. We could just run simulations, but we don't want to think a little bit, right? We really want to have a better way of updating parameters than running a whole simulation, tweaking parameters. I mean, this is stochastic optimization with no gradient, right? We could do that, and people have done it, but we'd like to do something better. And so we have some learning rules like this. And like I say, in real biological systems, this is done by random mutations. But at least for the learning rule, we can do something smarter. And this is what in Benzier's 1991 paper, which my very smart postdoc rediscovered, my other very smart postdoc rediscovered, which is learning the learning rule. And it's really, the idea is pretty simple, right? In hindsight, let C be the cost associated with a particular set of weights. We're kind of used to that. Sort of an average of the cost over all the training examples. And the learning rule, right, we let W go to W plus delta W. This is what I F here. It depends also on activity, but I'm just writing the theta dependence right now. And we can differentiate with respect to theta, right? That's dC dW, not dW delta W d theta. This is our learning rule. And that's backprop, right? which, of course, so far has, in my mind, there are no biologically plausible implementations of backprop in the brain. But in this case, we get to use it, right? Because we're just after the good parameters. We don't care, and we're thinking the way they got there is basically some very stochastic, on evolutionary timescales with small tweaks. But we can, because we just care about the parameters, we can run this, and this is our learning to learn, right? So if we have a good parameterization of our learning rule, we can actually run this, and it's much, much faster than having to go through evolution, okay? So we actually did this, a sanity check is perceptron, right? So we know what the answer is going to be. So perceptron, that's y, and we train on XY star pairs. And this is our parameterization, okay? So, oops, this should not be to the nk. That should not be there. Basically, we had, depends on x, l, and y star. So y is the actual output of the network, y star is the true value, and m, l, and s were in some range. I think we actually went up to 3. And that includes the perceptron rule, right? That would be, falls in this class because of the sum, right? And so we just optimize with respect to theta, and it usually works, right? But it takes a long time. It's much slower than backprop, obviously, or much slower than the perceptron rule. But it works sometimes. But interesting, sometimes it just doesn't, right? Which is possibly a little bit worrisome, but maybe not so surprising, right? We haven't done a lot of analysis for this. We don't know why. In this case, it just didn't work. Okay, it's a little bit surprising. I guess in the era of deep networks, we're used to everything working, right? Well, except for maybe Shay yesterday told us examples where it didn't. So we don't really know what's going on there. But at least we're not obviously wrong. And in fact, this was, again, this is a danger of starting a new project. This is one of the reasons I hesitate talking about it, because who knows what's been done. And the more we read, the more we find out what's been done. But again, it seems like nobody's followed this up recently. So I'm mainly done. Mainly done-ish. So let's recap. So we've taken a rather old idea, genetic algorithms, with a small twist, right? And usually genetic algorithms, you have a mutation and something happens. Now we have a mutation and we learn based on a learning rule, then we have another mutation. But it's not a huge twist. Our very long-term goal is to skip the genetic part of the genetic algorithm, right, and make the generational rule, the generalization update rule differentiable, right? Differentiable is the catchword these days, so that we can learn a lot faster and get to these parameters much more quickly. And for the learning rule, so this we're done. We know how to do that rather efficiently. So the deep learning community is working on this one. We could steal their idea. It's just architecture, maybe hyperparameters. And I believe this is new, which means I haven't yet found somebody else doing it, at least in this particular context. And we might ask sort of, the simplest thing, what's the glaring weird thing about the brain excitatory and inhibitory neurons? At least conceptually, this should give us a path for explaining this, right? Because it had the potential to explain excitatory and inhibitory neurons, and I think kind of it maybe does. This is the most speculative part of this talk. So the genome has enough bits to specify the initial mean weight in a particular group. Okay, we saw this earlier. It's like this. So all the sort of means in there are the same, less noise. But one of the things that these networks have to do that we don't worry about when we build artificial networks is they have to kind of work from birth. Okay? I mean, although humans are useless blobs, they actually, first of all, they learn very rapidly. Second of all, they can do stuff, right? They can follow their eyes, move their arms, and eat, breathe, and other things. Okay? And so this is the speculative part. The mean weights probably have to be mainly either positive or negative. Okay? If the mean weights are 0 from one group to the other, nothing is really going to happen. So, and you can imagine with several hundred different areas, if you count layers, because you probably have on the order of 1,000 different areas in your brain. If you set the connectivity so it's either positive or negative, you may actually be able to do something reasonable. Okay, that's a fair number of parameters, and you don't have to do much as a very small child. Now, it'd be kind of interesting in species that do very well to see if things are different. Say it again. So the mean from here to here, the mean connectivity from here, from one group to another, or within a group. So this is massive speculation, right? And that would, as a first pass, explain excitatory and inhibitory neurons. But of course, why can't the weights change with learning? And here, so that we can go back. This is a synapse, right? You can imagine having an excitatory synapse. It's got AMPA receptors there. If you want to make it inhibitory or make it change sign, the way biology works, and who knows where this constraint came from, you kind of have to add other receptors, right? And there's an information cost in the genome of doing that, on the order of a bit times something. So let's add that. So given that weights need to start out positive or negative in the average, it just may not be worth it. Okay? It's a bit of a stretch, but I think it's got potential. This bit constraint, I think, is ultimately going to have potential for explaining some of these things. So I wrote the bound like this. In fact, it looks like this. Okay? And I see this as an important constraint. It's often overlooked in the deep learning community for good reason, right? They don't have this constraint, but biology does. Okay, I'm going to mention three. I mean, there's tons of open questions because we barely started this work. There are three really, really big ones that I see. One is, how do we parameterize the learning rules? Okay, so I wrote it like this. It's sort of the simplest possible learning rule, but I talked about this a little bit with Larry the other day. And as he pointed out, we'll probably need to put in long time scales, including some memory trace. I mean, and this is hard, right? Because we're parameterizing some function we have to kind of guess. So it's not going to be an easy problem. I think in the early problem we're going to consider, where we have just simple input-output functions, this is going to be enough. But if you ever want to solve some of the interesting problems in which reward comes at the end, we may need much more complicated learning rules. And it's a little bit of an art, as usual, deciding what the parameterization is. And the other one is, second one is, how do we efficiently optimize with respect to initial conditions? Okay. It's not so easy. So, I mean, a couple examples, a couple cases. One, if we shift initial conditions a little bit and we end up close by, it's going to be a relatively easy optimization, right? Derivative here is going to correspond to derivative up there. Modulo, I mean, easier, right? This is an easier case. On the other hand, things may be massive chaotic. You may end up way over there. That's going to be very, very hard. And we don't really want to be in a position of, simulating a network for 10,000 trials and tweaking a parameter a little bit. So we need a smart way to efficiently update initial conditions, and I don't at this time know what it would be. Architecture, I think, is a little bit easier. And this is something I alluded to in the beginning. What task should we give our network? Okay. More concretely, what input-output function? And here's my dream. Okay, which is a little bit shot down by the talk yesterday. I want to consider a model where X comes from a relatively complex hierarchical model, where L is a latent variable, and X is our thing. We saw this Tolley's. This is Tolley's picture in the beginning, right? So the thing you want to learn is sort of low bit rate, and it gets spread out in this very complicated way. Another parameter. And the output is going to be a function of the latent variable, right? Like the worst output for learning in the world. And this is Shay mentioned earlier, Shay or Shai? Shai. So I mentioned earlier, this is very, very hard to learn. Of course, we've been evolving for 3.8 billion years, so it's possible. And so, there are several ways to solve this, right? You may be, depending on the structure, you may be able to sort of work out how to put the output. So by the way, this more or less corresponds to the output, to the feedback signal organisms get, right? Our actual feedback signal is really, really sparse. So the zeros in here is because a lot of times you get no feedback at all, right? Bit rate for supervised feedback is bits per day, right? Every now and then it's high when you grow up, but you burn your hand or somebody yells at you, right? It just doesn't happen very often. And we'll network learn a generative model. Okay, and if it does, I swear I'll die happy. Okay? And I'm not the only one thinking about this problem, right? But this is something that's really, really, I'm not sure bother is the right word, but we always build these models of generative models in the brain. The brain doesn't work like that. It just evolved these structures, and how did it do it based on this super sparse feedback signal? But you solve this problem, you solve a lot. Okay, so now I really am done. I think that was kind of short. This talk has been mainly about ideas, not results, hopefully not completely trivial. So I've outlined a program which I think will be useful for understanding the structure we see in the brain. And And along the way, we may learn lots of other things. I mean, my experience is if you really deeply understand anything, you always understand something interesting. And so you ask you have this big question, right? So the system developed resources to initial conditions, groups, or learning rules, right? And how that's traded off, and why? Maybe that'll explain some of the diversity we see in species, and we can look at reasons why. And you can sort of imagine in a super stationary environment, right? There's no reason to even have learning rules. And sort of your effective stationary environment may determine the kind of learning rules you need. And so far this work, as you've seen, has been incredibly preliminary. It's been going on. I've been thinking about it for maybe a couple of months, but we've actually started doing things about a month ago. And the hope is that if we beat our heads against the wall long enough, we'll gain analytic insight. I don't know about you guys. This is how I do science, right? You stare at a problem, you stare at a problem, you stare at a problem, and something eventually pops into your head. It's a little worrisome because you never know when or if it's going to happen. Okay, so I want to thank the main collaborator, and this is Naoki Hiratani, postdoc at Gatsby. I put Alex Pouget in gray because we've been talking about this, but I don't want you to blame anything for it. We shouldn't blame Naoki for anything in this talk either. And also, of course, for the very generous funding from the Gatsby Foundation and more recently from the Wellcome Trust.
So can I ask you about your example with the perceptron? So I wasn't sure quite what the error was. So did it learn the perceptron?
It didn't learn exactly the perceptron rule. Presumably if we ran long enough, it would have, although there's... but yeah, it didn't quite line it.
Learned the rule that worked.
Learned the rule that worked pretty well, yeah.
It wasn't necessarily...
Yeah.
So I was confused by so the cost function, in the end, it's really a dynamic cost function across the whole trajectory.
Yeah, I said.
You're just, in your optimization rule, you're optimizing like a recurrent network.
We've done one set of simulations. We're looking at recurrent connectivity now. The simulation we've done was perceptron rule. So.
No, I didn't mean recurrence to connection. I mean the recurrence to the learning rule. So if you say essentially you're going to apply 1,000 rules on a given life, and then you'll get like the same. So you'd like to say what my optimum parameters for learning rule are, not based greedily on how much improvement I can make in my cost function in one step, how much I can make in that.
So the cost function, so we have to kind of define it. So the cost function I defined was sort of the average crossover out of the trials. But you're right, so maybe you want to weight more heavily how you do at the end. Is that what you're talking about?
No, the learning rule you get, your big aim is learning, then you can learn. Yeah.
So right now we fix, so right now simplest possible case, we fix the learning rule, it's going to be the learning rule. You should probably weight how well you do at the end versus the beginning. You might want to, there are lots of ways to do this, but yeah. So that would be a more complicated parameterization of the learning rule.
So generalize the issue about stopping. We have to stop the learning rule as well as stopping.
Yeah, so you could evolve the learning rule in time too. I mean, and sort of the sky's the limit on what you can do. We can start off simple, and we know actually the learning rule changes with, nobody's really studied this because mainly they look at learning rules early on, but learning rule probably changes over our lifetime.
No, we actually just like correlation systems change learning rules as you go.
Yeah.
As you have motivation.
Yeah. So in the long term, yes. In the shorter term, we're going to start off very, very simple.